Welcome to another live session of our assumption physics reading group. Today we're going to continue with the logic of verifiable statements. We had defined what a experimental domain and a theoretical domain were, and last time we basically characterized any theoretical statement as being made of three parts. The part that is verifiable, falsifiable, and undecidable. And so we'll continue with those and see where we get. So let me share the text. Share. There we go. And let me put, as usual, the link in the chat. There might be a problem with the change of daylight savings time. In the US we changed, in Europe we haven't. I don't even know what's happening in other parts of the world, so it is what it is. Okay, Tobias, would you like to start?
Sure. I don't know why my video is not working. I can turn it on, but I can read. Okay. The theoretical domain then contains all sorts of edge cases. Similar to undecidable statements, we could have statements that can just never be verified experimentally. That means the verifiable part of S is false.
Is impossible.
Impossible. Or just never falsified. So the falsifiable part is impossible. The possible presence of these types of statements means we have to be cautious in giving physical significance to all theoretical statements, as the only thing we may be able to say about some is that nothing can be said about them. So footnote 18, it will be a recurrent theme of this work to make a precise distinction between mathematical objects that represent physical entities, for example, verifiable statements, those that represent idealizations of physical entities, for example, theoretical statements, and those that do not have scientific standing, for example, statements that are neither verifiable nor theoretical.
In particular, we want to be able to understand when two statements represent two distinct situations that we can tell apart experimentally. If the two statements are verifiable, for example, the mass is between 1 and 2 kilograms and the mass is between 2 and 3 kilograms, incompatibility will be enough to tell us that the two cases are distinct. Only one can happen at a time, since verifying one will be enough to exclude the other. If the statements are not both verifiable, for example, the mass is between 1 and 2 kg and the mass is exactly 2 kg, being incompatible is not enough. One may lie in the undecidable part of the other, in which case we cannot verify one and exclude the other at the same time. In that case, we would not be able to distinguish the two cases experimentally.
Sorry, I was unmuted. It's me again, right?
Yeah.
For two statements, S1 bar and S2 bar, to be experimentally distinguishable, then we need to have an experimental test that always terminates successfully in one case and always terminates unsuccessfully in the other. That is, we need to have a third statement S bar whose verifiable part is broader than one, e.g., the verifiable part of S bar is broader than S1 bar, and whose falsifiable part is broader than the other. So the falsifiable part bigger than S2, broader than S2. This way, if S is found to be true experimentally, we know that S1 may be true and S2 must be false. If S is found to be false experimentally, we know that S1 must be false and S2 may be true. If the test for S does not terminate, then both statements must be false. So we are in neither of those cases.
Sorry, just in the previous part, this broader, the sign for broader, is it strict, or it also allows to be, I have to say, equality?
Allows the equality, yeah.
Allows. Okay,
Yeah.
very well. Okay, so then we can go to the next page, please.
Yeah.
Yes, the definition. Let S1 bar and S2 bar be two theoretical statements. We say they are experimentally distinguishable if there is an experimental test that can tell them apart. Formally, we can find a theoretical statement S bar such that S1 bar is narrower or equal to verifiable part of S bar, and S2 bar is narrower or equal to falsifiable part of S bar.
So narrower also already includes the equal. It would be strictly narrower, the one that excludes it. It's
Okay,
like a
I strictly.
subset. It's something is a subset of itself, so you just say it's a subset, and it's a strict subset when you don't have the equal.
Okay, I see.
This is like in order theory, typically ordering includes the equal because it's much easier to use with that operation than the stricter one.
I see. Justification. Suppose we have an experimental test E constructible from those associated to D that can tell S1 bar and S2 bar apart. Then we must have that without loss of generality. The result of the test E and the truth assignment A is a success for all A in possible assignments for which A of S1 is true and the result of the test and A is failure for all A in assignments for which A of S2 bar is true. Okay, sorry, that was a long one. Without loss of generality, we can take E to be an optimal test since we could make it optimal by combining it with other tests. Let S bar be a statement associated with that optimal test. Then we have that S1 bar is narrower than verifiable part of S bar, and S2 bar is narrower than falsifiable part of S bar. This justifies the definition. And then proposition 45, two theoretical statements, S1 bar and S2 bar, are experimentally, which are undecidable, are experimentally distinguishable if and only if we can find two verifiable statements, S1 and S2, such that so S1 is not equivalent to S2, or
They are incompatible. They can't be true at the same time.
okay, so that S1 and S2 are incompatible. S1 bar is narrower than S1, and S2 bar is narrower than S2. Proof, let S1 bar and S2 bar be experimentally distinguishable. Then we can find S bar such that S1 bar is narrower than verifiable part of S bar, and S2 bar is narrower than falsifiable part of S bar. Moreover, verifiable and falsifiable parts of S bar are incompatible. Therefore, verifiable and falsifiable parts of S bar are verifiable statements that satisfy the condition in the proposition. Conversely, let S1 and S2 be such that S1 and S2 are incompatible. S1 bar is narrower than S1, and S2 bar is narrower than S2. We have that S1 bar is narrower than S1, which is equivalent to verifiable part of S1. And we also have that S2 bar is narrower than S2 and is narrower than falsifiable part of S1, because falsifiable part by definition is broader than all verifiable statements incompatible with S1. Therefore, S1 bar and S2 bar are experimentally distinguishable.
To sum up, verifiable statements are the only ones that, perhaps under some simplifying assumption, we can think of as tangible scientific objects. For example, the idea that we can measure mass with finite precision. From these, we construct theoretical statements that represent our idealizations. For example, the infinitely precise value for the mass of a particle or the idea that stat value is a rational number expressed in a particular unit. And then there are statements that are not even physically meaningful, as they have no well-defined experimental consequences.
We
Maybe
have seen,
Sorry.
maybe I read and then you can go with propositions. We have seen that the theoretical domain may contain more statements, but we want to make it clear that it never contains more information. That is, if we knew which verifiable statements were true and which weren't, we would automatically know which theoretical statements would be true or not. So it is not adding extra cases. It is essentially completing the list of answers by adding a no if only yes can be experimentally verified, and vice versa. To see that this is the case, we can show that a basis for an experimental domain D is also a basis for its theoretical domain D bar. That is, all verifiable and theoretical statements can be expressed as functions of the same basis. The difference is that a theoretical statement can be a function of the negation of the element of a basis.
Okay, proposition 46. The truth values of the statements of the basis B for an experimental domain D are enough to determine the truth values for all statements in the associated theoretical domain D bar. More formally, all statements in the theoretical domain D bar can be generated by negation, countable conjunction, and countable disjunction from a basis of D. Proof: by definition of basis, any verifiable statement within the experimental domain D can be generated from B using only finite conjunction and countable disjunction. The certainty may be generated through negation and disjunction from any verifiable statement. Therefore, B generates D, which in turn generates D bar by definition. This means that B, through negation, countable conjunction, and countable disjunction, generates all of D bar.
Having defined what a theoretical domain is, we can finally define what the possibilities of a domain are. Those statements that, if known to be true, determine the truth value of all other statements. Definition: a possibility for an experimental domain D is a statement X in D bar that, when true, determines the truth value for all statements in the theoretical domain. Formally, X is not equivalent to impossibility, and for each S in D bar, either X is narrower or to S than S, or X is incompatible with S. The full possibilities, or simply the possibilities, X for D, are the collection of all possibilities. Yes.
I think I should have added a justification here, but the point is that the possibility can't be impossible. That kind of makes sense. And for any statement, if X is narrower than S, it means that if X is true, S is true. And if X is incompatible with S, then if X is true, S must be false. So if you know what X is, if X is true, right? If you know that one X is true, then you know that all the statements, all the other statements, which one are true and which one are false.
Okay. A possibility represents a complete answer for a scientific question. Only one of them can be true, and one of them must be true, since the theoretical domain contains all negations. But how can we construct them? Suppose D is the experimental domain for animal species identification. There will be a set of possible truth assignments for it. Suppose B is a subset of D. Well, it's a basis of statements, like that animal has feathers, that animal has claws, that animal has paws, and so on. That allows us to fully identify the animal species. Then each possible assignment for the base will correspond to one and only one assignment for the domain. Consider A minterm, a conjunction where each statement appears once either negated or not. For example, that animal has feathers and that animal has claws, and not that animal has paws, and so on and so forth. If that statement is true, it will determine the truth value of all the bases. It will select one possible truth assignment for the whole domain. Then a possibility for the domain is simply a minterm of a basis that corresponds to a possible assignment for the domain.
Okay, proposition. Let D be an experimental domain. A possibility for D is any minterm of a basis that is not impossible. Proof. Let B be a basis for D, and let X be a minterm for B. Any theoretical statement S in D bar can be expressed as the disjunction of minterms of B, yes, by 126 and by 146. X is either within the minterms needed to express S or not. If it is, then X and S is equivalent to X, and therefore X is narrower than S. If it's not, X and not S is equivalent to X, and therefore X is incompatible with S. Therefore, a minterm is either narrower or incompatible with all theoretical statements, and if it is not impossible, it is a possibility by definition. Conversely, suppose X in D bar is a possibility. As it is a theoretical statement, it can be expressed as a disjunction of minterms of a basis B. Suppose it is the disjunction of more than one minterm. Then each minterm would be narrower than X, which cannot be. X must be expressed by a single minterm. Therefore, any possibility is a minterm. And yet another proposition, no other possibilities, states that all statements that determine and only determine the truth value of all statements in theoretical domain D bar are possibilities of D. Formally, there is no statement as that has all the properties of a possibility except that S is not in D bar. Proof. Let X be a statement that determines and only determines all truth values of all statements in a theoretical domain. This is equivalent to determining the truth values and only the truth values of all elements of a basis B in D. As we can find a countable basis, the statement X is equivalent to the countable conjunction of statements of B or their negation. Therefore, X in D bar, as it is generated by the statements of the basis by negation and countable conjunction. But a statement in D bar that determines all truth values of the statements in D bar is a possibility by definition. Therefore, X is a possibility.
Yeah, so this last thing is to just make sure that there is nothing else in the full domain that we're missing and in the full context that we're missing. And so it basically tells you that there isn't anything that we're missing.
There is one possibility that is often forgotten and sometimes needs special handling. Suppose one is trying to identify an illness by going through a series of known markers. It may happen that no match for the disease is found because we are dealing with a new kind of illness. In the same way, we may fail to measure the value of a quantity because it lies outside the sensitive range of our equipment. In other words, it may be possible that none of our tests succeed and none of the verifiable statements is verified. We call this possibility the residual because it's what remains after we went through all the cases we already know.
Note, though, that the residual possibility does not exist for all domains. Suppose we have a basket of fruit and we want to count how many whole apples there are. There can only be a finite number of them, and we can successfully identify all finite numbers. There is no something else to be found in this case. And then we have the definition. The residual possibility X dot for an experimental domain it is, if it exists, the possibility that predicts that no test will be successful. formally, let B and D be a basis, then X dot is conjunction of negation of test for all possible, no. Is it negation of test or of basis elements?
Of all the basis elements, yeah.
So conjunction of all, negation of all basis elements, if it is not impossible. An experimental domain is complete if it doesn't admit a residual possibility. And the definition, the established possibilities, X big dot is X, how to say, modulo the singleton of X dot for an experimental
Minus
domain.
the X
Minus,
dot,
yeah.
X circle.
Yeah, X circle. For an experimental domain is the set of all possibilities excluding the residual possibility.
Yeah, so this residual possibility is something that I had to define because later you want to show that two domains, when you're making when you're combining them, they form the coproduct, and so there is this case that you have to add that behaves in a different way, and yeah, so it's kind of a word. I wish I didn't have to define this, but that's how it works. It's when you basically have you want to later combine the domain, let's say, of plants and of animals, so that then you make the domain of both plants and animals. Then you need to allow the possibility that when you were doing plants, you had something else that wasn't a plant, and when you had animals, you had something else that wasn't an animal. So that when you put them together, they combine, correctly. So that's basically what it is.
Okay. As we refine our understanding and techniques for domain of knowledge, we may find that the residual possibility actually corresponds to multiple cases that weren't previously cataloged. So intuitively, it is better thought of as a bucket that contains all that is yet to be experimentally discovered within the particular domain of knowledge. Because of its special nature, the residual possibility sometimes behaves differently than the other possibilities. Therefore, we will find that some theorems are more elegantly expressed in terms of the established possibilities and some in terms of the full possibilities.
So to sum up the mathematical structure of the domain, consider the following table. Yes.
Okay, so this is the basis. This is the experimental domain. This is the full domain. And these are the possibilities. Now, in principle, the possibilities could be part of here and could be part of the experimental domain, but I put them separately just to show you sort of how the truth value work.
Right. On the left, we find the basis elements. From these, through finite conjunction and countable disjunction, we construct all verifiable statements. From these, through negation, countable conjunction, and countable disjunction, we construct all theoretical statements. And within these, we find the possibilities. Each row corresponds to a possible truth assignment for the domain. Each possibility is true in one and only one possible assignment. The mathematical structure then is simply there to keep track of the logical relationships between all the statements, which assignments are possible and which statements are verifiable.
Yeah.
With our definitions in mind, we can answer the following fundamental question. What is the maximum number of possibilities that an experimental domain can have? In other words, what is the maximum number of cases from which we can distinguish experimentally? As we saw before, a possibility is a statement that defines the truth values of a basis. Since a basis is countable, we can uniquely identify a possibility by a countable sequence of true or false. Note that a real number expressed on a binary basis, e.g. 0.1, 0.010, so on, will also be uniquely identified by such a sequence. The cardinality of the possibilities is at most that of the continuum. So we turn that into a theorem. The possibilities X for an experimental domain D have at most the cardinality of the continuum. The proof goes like this. Let B be a countable basis. Let 2 to the n denote the set of infinite binary sequences. We define the function f from the possibilities into Boolean sequences. I guess that's the same as 2 to the n, right?
Yeah, so I should have put yeah, so I should have either used 2 to the n or b to the n in
Yeah, okay. I would just say that they're the same, but okay.
yeah, let me make a note. Okay.
So f of x returns a sequence of 0 or 1 or true or false. And it tells me whether, okay, and the ith element tells me whether basis element I is true or false.
It's compatible or incompatible.
Compatible or incompatible. Okay, yeah. Okay, whether f returns true or false tells me whether the particular basis element is compatible or incompatible with that possibility. So for each possibility, we have its decomposition in the basis, where I guess the coefficient, whether we negate or not, is given by f.
Yeah.
Okay. Suppose we have two possibilities, two x that are distinct, then f of x will also be different for some I. Therefore, f is injective. We then have, since it's from x to 2 to the n, that the cardinality of x must be less or equal to the cardinality of 2 to the n, which is the cardinality of the continuum. X has at most the cardinality of the continuum. Yes.
This means we have an upper bound on how many cases can be distinguished experimentally, only up to the continuum. We are not going to be able to tell apart experimentally more possibilities than those. This result gives us a basic requirement for any mathematical object we want to use in a scientific theory. If the cardinality is greater than the continuum, it cannot have a well-defined experimental meaning. For example, while the set of all continuous functions between real numbers has the cardinality of the continuum, the set of all functions, including discontinuous ones, has a greater cardinality. We can already conclude that the first set may be useful to represent physical objects and that the second may not. Yes, as we are looking into the cardinality of the possibilities of a domain, it should not be surprising that the only way we can have infinitely many possibilities is if we are given infinitely many verifiable statements, as each verifiable statement can distinguish between two cases, true or false. We need infinitely many of these distinctions to reach infinitely many cases.
Let dx be an experimental domain. Then the following are equivalent. The set of possibilities is finite. The experimental domain contains finitely many verifiable statements, and there exists a finite basis. To prove that, we prove 2 from 1, so finitely many verifiable statements, based on the fact that we have finitely many possibilities. Let dx be an experimental domain and x is possibilities. Suppose x is finite. since any statement in dx can be generated from x using finite conjunction, dx must be finite as well. Okay, finite conjunction, finally many elements.
Okay, so the combinatorial,
Yeah, to prove 3 from 2, there were finite bases based on finitely many verifiable statements. Let dx contain finitely many verifiable statements, then a basis will consist of finitely many statements as a subset, the domain, and then we prove 1 from 3. So we start with a finite basis. Since the possibilities are min terms of the basis, we have that x is bounded by 2 to the b. B is finite, has finite size, then 2 to the b is also finite, and then x is finite.
We have now presented the fundamental objects of our general mathematical theory of experimental science. In our framework, a scientific theory or a scientific model is an experimental domain, a set of statements, what they mean, and how to verify them experimentally. The starting point is often a basis, a set of verifiable statements which defines all the domain knowledge that we can gather experimentally. The content of the statements determines what combinations can be true at the same time, which defines the possibilities for our domain. Everything in the domain is grounded within the verifiable statements. There is nothing else in it. This also maps well to the practice of most scientific fields, where one defines states and other physical objects based on what can be measured.
And as we'll see later, some verifiable statements may be idealizations. For example, we may assume that a quantity can be measured with arbitrary level of precision, which we know not to be strictly true. We may assume a volume of gas to have a well-defined temperature, which may not be true if it is not at perfect equilibrium. This type of simplification makes a domain applicable only within the realm of validity of those idealizations, but does not change the formal structure we have identified here. In fact, the focus of much of this work will be deriving the details of different experimental domains under different physical assumptions. The main point of our framework is that this conceptual structure is inescapable once we set the principle of scientific objectivity. We will always need a set of statements and a way to test them. And if we are given those, we have all we need. These elements are necessary and sufficient to be able to do science. And by being clear about which statements can be considered physically meaningful and which are the idealization, we can then be more precise on the physical status of each component of a particular scientific theory.
Okay, so I don't know if there are any questions on this. Then we basically are going to, I think we should be able to do it all today. We're going to map all that we have said in this last few times to topological spaces. So we basically are going to see that experimental domains are topological spaces.
All right, topological spaces. Now that we have defined what experimental domains are, we want to explore the link between them and some fundamental mathematical structures. The main result of this section is that an experimental domain provides a natural topology for its possibilities. Each verifiable statement can be seen as the disjunction of a set of possibilities. Performing finite conjunction and countable disjunction of verifiable statements means performing finite union and countable intersection of those sets of possibilities. Topological spaces were developed in the first half of the 1900s as a generalization of metric spaces. The idea is to define a notion of closeness without having to define an actual distance. We have a footnote. In science and engineering, one talks about topology also when discussing the structure of a molecule, an electronic circuit, or a computer network. These types of structures, nodes connected by vertices, are studied by graph theory and should not be confused with point set topology. Yeah. Other branches of math, for example, metric spaces, differential geometry, Lie algebras, now see their foundation on topological spaces, which therefore play a very important role in mathematics as a whole. In our case, this notion of closeness will map to how hard it is to tell the possibilities apart. That is, possibilities that are topologically closer are more difficult to distinguish experimentally.
Let's first review what a topology is. The general idea is that we have a set X of elements, which we call points, and a collection of subsets of X, such that it is closed under finite intersection and arbitrary union, contains the empty set, and contains the whole set X. For example, suppose X is just a set 1, 2, 3. Then the set of the empty set, singleton 1, singleton 2, and the full set is not a topology, while if we have the empty set, singleton 1, singleton 2, their union and the total set is. The first one is missing this union. So definition 54, let X be a set. Topology on X is a collection Tx of subsets of X closed under finite intersection and arbitrary union such that it contains X and the empty set. A topological space is then the tuple X and this topology. Yeah, the set and the topology defined on it.
Mathematicians designed this abstract mathematical structure because it is a useful and general tool to study the notion of continuity. It also happens that all the mathematical structures used in science are topological spaces. Why is that? Why is it that what is that topological spaces capture? Let's go back to our verifiable statements and possibilities. For example, consider statement 1, the mass of the photon is less than 10 to minus 10 electron volts. This can be expressed as one being this junction. The mass of the photon is precisely x electron volts, where x is between 0 and 10 to minus 10. The precise value must be in the given range of possibilities. Consider a statement as 2, the mass of the photon is greater than 10 to minus 20 eV, which is equal to the disjunction of the mass of the photon is precisely x eV, where x is greater than 10 to minus 20. The conjunction is the intersection of the possible values S1 and S2. The mass of the photon is between 10 to minus 20 and 10 to minus 10 eV, which is the disjunction of statements. The mass of the photon is precisely x eV, where x is between 10 to minus 20 and 10 to minus 10. The disjunction is the union of the possible values, S1 or S2, as the mass of the photon can be anything, which is the disjunction of the mass of the photon is precisely x eV, where x is anything greater than 0.
This is something that works in general. In proposition 26, we saw that if a statement is a function of other statements, it can be expressed as a disjunction of minterms of the arguments. A verifiable statement is a function of the basis, so it can be expressed as the disjunction of minterms of a basis. But we have also seen that the minterms of a basis are the possibilities, so each verifiable statement can be expressed as a disjunction of possibilities. Therefore, each statement in the experimental domain defines a set of possibilities, which we call a verifiable set. Since certainty and impossibility are in the domain, the empty set and the full set of possibilities are verifiable sets. Since we can take finite conjunction and countable disjunction of verifiable statements, we can take finite intersection and countable union of verifiable sets. The collection of all verifiable sets form a topology on the set of possibilities.
Okay, so we have a number of definitions and propositions.
Yeah.
Okay, let D be an experimental domain and X its possibilities. We define the map U from the domain to X that for each statement S in D returns the set of possibilities compatible with it. That is, U of S is equivalent to the set of all possibilities that are compatible with S. We call U of S the verifiable set of possibilities associated with S. Proposition. A statement S is equivalent to the disjunction of the possibilities in its verifiable set U of S. Yes, that is S is equivalent to the disjunction of all these X's in U. Proof. First, we show each statement is the disjunction of some set of possibilities. Let D be an experimental domain, S in D be a verifiable statement, and B subset of D a basis. Since S is a function of the basis, it can be expressed as a disjunction of minterms of B. The minterms of B that are impossible can be ignored since S or impossibility is equivalent to S. But the minterms of B that are not impossible are possibilities of D. So S is a disjunction of X's in U for some U as a subset of X. Now we show it is the disjunction of its verifiable set. Let X be a possibility and consider X and S. If X is in U, then X and S equals to X and the disjunction of X's in U, which is then the disjunction for all of X and X hat for all X hat in U, which is equivalent to X, which is not equivalent to impossibility. Therefore, X is compatible with S. If X is not in U, then X and S is equivalent to impossibility. Therefore, X is incompatible with S. This means that U is U function of S as it contains and only contains all the possibilities compatible with S. And another proposition, let X be the set of possibilities for an experimental domain D. X has a natural topology given by the collection of all verifiable state sets. T of X, that is a function U of a domain D. Proof. The verifiable sets for the certainty and the impossibility correspond to the full set and empty set respectively. Formally, U of certainty is a set of X for of all X's in the possibility set where X is compatible with certainty, and that is equal to X. While U of impossibility are all the X's in the possibility space where X's are compatible with impossibility, and hence it's an empty set. Therefore, the full space and the empty set belong to U of D, since both certainty and impossibility are elements of D. The finite intersection of verifiable sets corresponds to the verifiable set of the finite conjunction, and therefore it is a verifiable set. Formally, U of S1 and S2 is a set of all X's such that they are compatible with S1 and S2. Then it equals to all the set of all X's such that X is compatible with S1 and X is compatible with S2, which is equal to the set of X's where X is compatible with S1. Intersection, yes.
Mm-hmm.
an intersection with another set of x's where x's are compatible with S2, which equals intersection of U of S1 and U of S2. The countable union of verifiable sets corresponds to the verifiable set of the countable disjunction, and therefore it is a verifiable set. Formally, U of S1 or S2 equals the set of X where X is compatible with S1 or S2, which is equal to the set of X where X is compatible with S1 or X is compatible with S2, which equals to the set of X where X is compatible with S1 union with X with a set of X's where X is compatible with S2, which equal the union of use of S1 and S2 respectively. This generalizes to countable disjunctions. Arbitrary disjunctions can be re-expressed as countable disjunctions, since any verifiable statement can always be expressed in terms of a countable basis. The collection D sub X is U of D is therefore a topology by definition, since it satisfies all its properties.
Yay!
Okay, mainly for historical reasons, the sets in a topology are called open sets. The complements of open sets are called closed sets. In metric spaces, such as the Euclidean space with the standard topology, these will map to the standard notion of open and closed intervals. Okay, but in general, they do not, and this may lead to confusion. For example, if we take the integers with their standard topology, any subset is both open and closed. Given that we are only interested in the natural topologies of possibilities, we are going to refer to the sets in our topology as verifiable sets, and we will occasionally call falsifiable sets their complements. For example, when counting apples, a subset of the integers is both verifiable and falsifiable. We can test whether the apple count is within or outside that set of possible numbers. While this terminology does not follow math convention, we find it more intuitive and meaningful in the context of this work.
We can also re-express the semantic relationships between statements in terms of set operations on the verifiable sets. For example, that animal is a cat is narrower than that animal is a mammal, because the set of possibilities for which the first is true is a subset of the possibilities for which the second is true. Conversely, that animal is a cat and that animal is a dog are incompatible because the set of possibilities in which both are true is empty. In the following table, we summarize how statement, operations, and relationships are expressed in terms of operations and relationships between sets of possibilities.
Yeah, so conjunction becomes intersection, and disjunction becomes union, as we saw. Negation becomes complement. The verifiable part is the topological interior. The falsifiable part is the topological exterior, and the undecidable part is the topological boundary. Equivalence means equality of the set. Narrower than means that you have a subset. Broader than means that you're a superset. And compatibility means that the intersection is not empty. So you can go from one to the other, and they're, they coincide.
Let's review the definition of basis and subbasis for a topology. A collection of sets from which we can generate the whole topology through finite intersection and countable union for a subbasis, or just through countable union for a basis. Sorry, a collection of subsets from which we can generate the whole topology through finite intersection and countable union for a subbasis, or just through countable union for a basis. Bases are important since they are often used in proofs and calculations. Moreover, many properties of topologies can be shown to be equivalent to properties of one of their bases. Countability, and in particular second countability, is one such property which characterizes the number of verifiable sets in a topology. So we define a collection B of subsets of of verifiable sets of X is a subbasis if every verifiable set in X is the union of finite intersections of elements of B. It is a basis if every verifiable set in X is the union of elements of B. And then we define a topology for X is second countable if it admits a countable basis.
There is a link between the basis of an experimental domain and a subbasis of a topology. If every statement in the experimental domain can be constructed from a basis through finite conjunction and countable disjunction, then each corresponding verifiable set can be generated through intersection and union of the verifiable set corresponding to the basis. Therefore, the verifiable set corresponding to the basis of the experimental domain forms a subbasis in the topology. Since experimental domains must have a countable basis to make sure we can test any verifiable statement given enough time, the topologies we'll be interested in must be second countable.
Okay, proposition 60. Let X be the set of possibilities of an experimental domain D. Let B be a basis for the domain, then the collection of verifiable sets U of B union X forms a subbasis for the natural topology of X. Proof: since every verifiable statement of a domain can be generated by finite conjunction and countable disjunction from a basis B, its corresponding verifiable set can be generated by finite intersection and countable union from the verifiable sets U of B corresponding to the basis. Note that the certainty, though, is not necessarily the union of U of B. It is the domain, if the domain is not complete, the residual possibility is not contained in any verifiable sets. Therefore, U of B union X can generate all verifiable sets, including the one for the certainty, and is a subbasis. And then another proposition: the natural topology for the possibilities of an experimental domain is second countable. The proof says, since each experimental domain admits a countable basis, its verifiable sets form a countable subbasis for the natural topology. We can close the subbasis over finite intersection, forming a countable basis for the topology. Natural topology is therefore second countable as it admits a countable basis.
Another important property to classify topological spaces is the degree of separation of their elements. How well one can use verifiable statements to tell points and sets apart. Andrei Kolmogorov, or T0 space is one in which for every pair of points there is always a verifiable set that contains one but not the other. This property is significant because it allows all points to be distinguished through verifiable sets. A Fréchet or T1 space is one for which for every pair of points we can find two verifiable sets, each containing only one. In a Hausdorff or T2 space, the two verifiable sets containing the points are disjoint. This implies the uniqueness of limits of sequences of points. Okay, and I guess we have the definitions for these topologies.
Yeah.
So
it's exactly what
topology,
we said before.
yes.
If it's T0, then you can find one that contains one more of the other. I mean, this is just a mathematical. And the remark is the thing that is more important. If it's T2, then it's T1, and if it's T1, it's T0.
How do these properties relate to experimental domains? Consider two possibilities for a domain. For example, that is a cat and that is a swan. We can always find a verifiable statement such as that animal has feathers that we can use to distinguish one possibility from the other. This means that given two different possibilities, we can always find a verifiable set that contains one and not the other. The natural topology for any set of possibilities is always T0.
Now suppose two possibilities are approximately verifiable as we defined in definition 38. For example, the mass of the photon is exactly 0 electron volts, or the mass of the photon is exactly 10 to the minus 20 electron volts. We can find two verifiable statements. The mass of the photon is less than 10 to the minus 25 electron volts, and the mass of the photon is more than that, each compatible with only one possibility. This means that given two approximately verifiable possibilities, we can find two verifiable sets, each containing only one possibility. If all possibilities are approximately verifiable, then the natural topology is T1.
Now suppose two possibilities are experimentally distinguishable as we defined in definition 144. Then by 145, we can find two disjoint approximations. In the example before, the two verifiable statements were in fact incompatible. This means that given two approximately verifiable possibilities, we can find two disjoint verifiable sets, each containing only one possibility. If all possibilities are experimentally distinguishable, then the natural topology is T2.
Yeah. So I don't know if we want to go. We don't have anything else. So if you want, we can go through the proofs. So the proofs are basically showing that they under those conditions you can recover the definition of T1, T0, and T2.
Well, we have 3 more minutes. Should we just
Yeah, let's just go through them quickly.
Okay. The natural topology of a set of possibilities is called Markov, or T0. So let X be the set of possibilities for an experimental domain. Then take two distinct possibilities. Each of them can be expressed as a minterm of a basis. Since the two possibilities are distinct, there must exist a verifiable statement in the basis that appears negated in one conjunction but not the other. That is, E is compatible with only one possibility. Since the verifiable set associated with the verifiable statement contains only the possibilities compatible with that statement, the verifiable set of E either contains x1 or x2, but not both. The topology is therefore 0 or cosmological.
The natural topology of a set of possibilities is Fréchet, or T1, if and only if all possibilities are approximately verifiable. Proof. Suppose all possibilities in X for an experimental domain D sub X are approximately verifiable. Let X1, X2 be two possibilities. Then we can find two sequences of verifiable statements, sequence of S1 and S2 in dx, such that X1 is a countable conjunction of S1s, and X2 is a countable conjunction of S2s. We can assume that sequences are monotone with respect to narrowness, that is, what is it? S1 sub I plus 1 is narrower than S1 sub I, as we can always create a monotone sequence from one that is not by taking the sequence of finite conjunction. That is S1 hat sub K, which is a finite conjunction of S1s if X1 is not equal to X2. Okay, if X1 is not equal to X2, then X1 and X2 is equivalent to impossibility, since different possibilities are incompatible. Therefore, we must have that X1 conjunction with S2 sub J is equivalent to impossibility, and S1 sub I conjunction with X2 is impossibility for some ij greater than 1, or the limits would be not incompatible. In terms of verifiable sets, we have X2 is not in U of S1 sub I, and X1 is not an element of U of S2 sub j. For any two distinct possibilities, we can find two verifiable sets, each containing one, the natural topology T1. Conversely, suppose the natural topology T sub x for the possibilities x for an experimental domain dx is T1. Let x be a possibility. Consider the collections, not necessarily countable, of all verifiable sets that are subsets of Tx such that they contain x. Consider their intersection ux, which is intersection of all ui's. It will contain x since all ui's contain x. It will not contain anything else. Since the topology is T1, for every other possibility x hat, there is always an open set u sub I that does not contain it. Therefore, u sub x is a singleton of x. Because the natural topology is second countable, we can find the countable basis B and rewrite the arbitrary intersection into singleton of x, that is what is it, countable conjunction of countable intersection of elements vi of the basis. Let S be the sequence of verifiable statements such that U of Si equals Vi for every I. Then X is a countable conjunction of Si's, which means that X is approximately verifiable.
Yeah.
Okay, let's just quickly wrap up. The natural topology of a set of possibilities is Hausdorff, or T2, if and only if all possibilities are pairwise experimentally distinguishable. Suppose all possibilities in X for an experimental domain dx are pairwise experimentally distinguishable. Then by 45, given two possibilities x1, x2, we can find two verifiable statements S1, S2, such that S1 is not compatible with S2. S1 is broader than X1 and S2 is broader than X2. In terms of verifiable sets, the intersection of their use are, well, they do not intersect, and then, or there are elements. The X1s are elements in the sets. The topology is T2. Conversely, yeah, we have something that does not intersect and contains each point. Conversely, suppose that the natural topology of the possibilities for an experimental domain is T2. Given two possibilities, we can find verifiable sets U1, U2 that are disjoint and contain each point. Since they are in the topology, we can find two corresponding verifiable statements in the domain that would get mapped using U onto these sets. Then we have that S1, S2 are not compatible. Okay, X1 is narrower than S1, X2 is narrower than S2. And by 45, the possibilities are pairwise experimentally distinguishable.
Yeah, so that's basically just mapping statements to sets, and there was nothing else so interesting. So that's basically it. So we mapped the notion of experimental verifiability to topology. We can go back and forth. And the next would be to do the same for the sigma algebras, and then there is a quick look at decidable domains in which all the statements are decidable, and then we finished the first part about topology. and then we should decide whether we want to continue or not, because attendance have been dwindling. So we'll see if these very technical mathematical sessions are interesting to other people or not. Any questions?
Maybe just a short question at the end. So we identified these three types of topologies, and well, namely, for example, this second countable is very important. Let's say in general relativity, when anyone just starts talking about the manifolds, this second countability is always there, unless it's a very pathological case. Now, having like this mapping with these with the experimental distinguishability, do you see why this would be preferred over other topologies, or is just really like just some choice for which like all of them are equivalently valid depending on what we want to achieve or what is possible, in a scientific process?
Yeah, it really depends. So they all have to be at least T0 and second countable. Because if you want to talk about cases that are defined experimentally, then you need at least one experiment to distinguish between 2 points. So at least you have T0. Actually, we had another live session with somebody else that argued that there should be a little bit more than T0 because of some other logic stuff. In fact, I wrote a note. We probably have to add it to do that. But at least it has to be 0. And it also has to be second countable, because otherwise you can't explore the space. This is the usual problem of, if you recall, we need the basis of the experimental domain to be countable, because we only have, let's say, we can only explore things in an arbitrary long amount of time, and so we can run at most countably many tests. And so we need the topology to be generated by these countable many tests, so therefore the sub-basis has to be countable, and so the whole space has to be second countable. So those things they have to be that. Then in different cases, you are going to have the separation axiom. So typically, most things that we are interested in turn out to be Hausdorff, because you can really tell things apart. And what we show in the ensemble spaces, for example, if we have if we are allowing for experimental science, not just observational science, so we have repeatability and we have ensembles, and the ensembles must have an entropy, then the entropy forces the space to be T2, to be Hausdorff, and all the limits have to converge. But it's not necessarily true. So for example, suppose that you have the question of how many fundamental particles are there. The only verifiable statements are of the form there exist at least n fundamental particle, because you can never rule out experimentally that there are more than 3, right? There are less than 3. You can say that there are more than 3 because you found 3 and you don't know if there are other things, but it's gonna be impossible to do that. And so for that, if you imagine the possibilities are the real, the natural numbers. There are 0 fundamental particle, 1, 2, 3, and so on. And all the open sets, so the verifiable sets are, the sets for which n is greater than some fixed numbers. And so you have all these verifiable sets that are sort of nested to each other. And that topology is not Hausdorff. Right? In fact, it's not even T1, because T1 would require that you have one set that contains one but not the other. But if you pick 2 natural numbers and the only things that you can, the only sets that you have is this number or greater, well, then one of them is going to include the other. And so you only have T0 and you don't have T1. So depending on which cases you have, you might have different domains.
Okay, so now I'm wondering if, let's say, I develop my theory for some law of physics, and now I'm asking various questions about this theory. So, depending on how I formulate the question, the topology will be different for the same physical theory. How to interpret this? Uh, and does it mean that there is, I don't know, different, I don't know, freedom to choose or parameterize if the questions are under different topologies in these cases?
Well, remember that a theory is the domain. So depending on what question you ask, you are going to have a different domain. So if you're
Mm-hmm.
asking the question, how many fundamental particles there are, right? That's one domain. But if you define the standard model, when you define the standard model, you told me which fundamental particles are there. So at that point, the fact that there are 6 quarks and there is an electron, muon, and so on, that's it becomes a certainty in your model because they say the model assumes these things,
Mm-hmm.
right?
I'm
But
just then.
the question of how many fundamental particles are there, it's a question that it's outside the standard model. It's basically asking whether the standard model is true or false. Because if you say that there are more than 6 quarks, then you
Mhm.
basically have said that the standard model is incomplete.
Okay, I'm just trying to understand, like, if we limit to one of these topologies, then does it mean that we are even like prohibited to ask a question about, I don't know, Lagrangian or dimensionality of the theory? Like, is that what it means? That if we add more detail, then we're limited to some topology and not all of them?
The topology is just defining, it's the same as defining which statement in your theory can be experimentally tested or not.
Hmm.
That's it. And so it, depending of what is it that you're trying to describe, you need to tell which statements are verifiable and which aren't.
Mhm. Okay, well, I mean, it's a very new approach towards understanding or interpreting these topologies. So maybe we'll see in the future how it works out. But
Yeah,
yeah,
but
so far it's very interesting point of attack.
it should be quite natural because whenever you have a real number, like the open intervals correspond to the thing that you can test.
Hmm.
Like the difficult things, and it's the things that I'm still working on, it's when you have infinite dimensional spaces, right? Because you need to understand which statements are actually, make experimental sense and which don't.
Hmm.
And that I still don't have a clear idea. But I know that there are in those cases there are really different topologies, and you would bump into problems if you assume the one as opposed to the other. So the fact, for example, if you have a space of the space of probability distribution, right? You have different way of converging. Different ways of converging means you have a different topology. And so depending on the topology, you're basically saying I can consider these two a sequence of verifiable statements that are converging to some point to converge to the same point or not. Right? So these things are linked to each other, and so properly defining your theory means properly defining convergence, which also means properly defining a topology, which also means properly defining what is it that you assume that it's verifiable experimentally or not.
Mhm. Okay, well, seems to be lots of stuff to do still to be done, but yeah,
Yeah,
sounds interesting regardless.
lots of detail. Okay, so we'll
Thanks very
stop
much.
and we'll check for next week.